This paper, titled 2 times faster language model pre-training via mass structural growth, is a pretty simple paper, has a pretty simple idea, but it's still kind of a cool idea nonetheless. Basically, the idea is if you start with like a smaller model, and then like a smaller model is fast to train, but it's not as good as a large model. It doesn't have as much capacity as a large model. But if you start with a large model, then it's a lot slower to train because there's a lot more parameters, and you have the optimizer having to optimize all those parameters. So what they do is they take a small model, they train that, and they slowly grow the small model into the large model. In this case, they use BERT. You can kind of see that here. They start off with a small model. That's not what I wanted. They start off with a small model here, and they slowly grow it, and they'll like train this model, and then they slowly increase the parameters over time, and it'll eventually lead to some larger model. In this case, this would be like BERT, maybe BERT B or BERT L. They use both in this paper, and you discretely increase it because the parameter count is a discrete number, and you discretely increase the number of parameters as training goes on. But there are some subtleties in this procedure that they point out. So yeah, we'll just get into how they do it. So if we look at this, let me erase my scratches. So I'll draw it on the right side over here. So we know in a transformer you have these tokens here. So you have some tokens, and you're going to throw this through some sort of layer norm. Maybe you're using actually we'll go with post norm in this case. So you throw this through some attention mechanism, and this would be a transformer. So we're just going to look at a transformer, and then you throw this through a layer norm mechanism while adding the residual. So you add the residual, then you throw this through a feed forward layer, and then another layer norm with a residual right here. So that's just a transformer block. Now, if we want to increase the number of parameters, the idea is, since a transformer is just using linear layers in all of its components, so the attention mechanism, it has 3 linear layers, one for the queries, one for the keys, and one for the values. The whole set is sent through each of these. And the feed-forward network is obviously a feed-forward network. And here you just compute the queries, keys, attention matrix. You multiply this by the values and get your output matrix. And then you also send this through another output layer if you have multiple heads. So our attention mechanism is just, our parameters are just a feed-forward layer, which makes this easy to deal with, and a feed-forward layer is also a feed-forward layer. Then we have layer norm, which is where other parameters come in, and that's one of the issues they had to deal with. But for now, if we just look at a feed-forward layer, it's really easy to kind of expand this. And there's a method that already does this called net-to-net. So basically, if you have this feed-forward layer here, so we have this feed-forward layer, it has parameters, so you have this like vector. In this case, this vector is I, this input vector with some values I sub 1 and I sub 2, I sub 1 and I sub 2. You send these through one layer, so this would be layer 1, and this would just be some weight matrix that you have. This is x sub 1, this is x sub 2, and you just have these weights here. So you have 4 weights here. This would be weight O, this would be weight P, this would be weight Q, and this would be weight R. And the second layer here is just the output of these weights, along with the this neuron here also has its activation function. So maybe that's a sigmoid. So like x1 would be equal to OI1, activation of OI1 plus PI2, and whatever, normal linear layer behavior. And then you have a second linear layer which will be important. We need to work with two layers, y2, and you have weights A, B, C, and D. So just a second layer, this would be layer 2. Now to extend this, it's pretty easy. You just add a second node here, and let's say we basically want to clone the bit. Well, the idea is you basically want to retain the function here. So our function here is you take these inputs, you send it through layer 1, and you send it through layer 2. And the idea is whenever you do the expansion, so you're expanding this or these two linear layers in some way, where the output y is the same as if you did it before expanding. And you want to retain this behavior so the models, because like if you already optimize a model, then the outputs here are going to be in some optima in the loss landscape. But whenever you increase the number of parameters, if you just arbitrarily increase the number of parameters, it will kind of change it won't be in an optima anymore. It'll just be in some random part of the loss landscape, and that can put it in a bad position where the optimization doesn't happen as well as you might like it to. So you need to initialize this in a way where the outputs are retained. And this way, the model starts off in the same spot as if it didn't have these parameters to begin with. So even if we add parameters here, it doesn't have to use them if it doesn't want to. It's probably going to because it will help it model the data it's trying to model, but it doesn't have to. And that's how we want to add the parameters, just in a way where the outputs are retained as before we added these. So to do this, just with one example, basically this is going from a space R2 to R3, except so like we have a two-dimensional vector and we're going to a three-dimensional vector for our weights. Now net2net does this in a way where we basically copy weights Q and R. So let's just arbitrarily copy one of these nodes, and it'll send, so we would basically copy these weights here, Q and R, and this function here, x2, this neuron here, or weight multiplication, is the same. So the output here and the output here will be exactly the same because the weights are exactly the same. Now to easily map this back to a function y, which gives us the exact same output as before we added this neuron, we can easily just map it back here, and you need to map this one to y1, and then just half the weights. So b would be b over 2, d would be d over 2, and then you copy the weights here, and this would be d over 2, and this would be b over 2. And this way this is sending half the information, and this is sending half the information. So you initialize this in a way, and they both send half the information, and the outputs y1 and y2 will get half the information from these two neurons, but since there's two neurons, then it just cancels out, and you get the same information. So this is one way of doing that, and that was the old way. But there's three problems with this that they talk about. So go here. So this was the previous method, and yeah, you can see you can arbitrarily grow this. So you have your old weights here, and your new weights are mapped in some way. You basically say you take your old weights, you leave them the same, and you take your new weights here and you map them to one of the old neurons here. So in this case, we mapped the new weight here, x2, to the old one, to x2. Or we took the new neuron, the new addition, and mapped it to x2, but we could have mapped it to x1 and it would have been equivalent. And you just divide the weights by the number of instances of that. So in this case, it was 2. But if we had a third, maybe we would just divide it by 3. This method is pretty obvious. So the biggest issue is layer norm. Now, if we have, so let's say we have this sequence here. Let me go back to this. So if we have a sequence here, A, B, and C, and we pass this through layer norm, then the way layer norm normalizes is over this dimension here individually, and then it would normalize over this dimension individually, or this like entire vector individually, and then it would normalize over this dimension individually, according to the statistics of that. So maybe our A vector has maybe it has the values like 1, 2, 3. That would make it easy. So it's a vector with 1, 2, and 3 in it. Then to normalize this, you just follow this formula here. So if you look at this formula, or we'll call this x because that is the same here. So if you look at this formula here, erase this, you basically normalize it by the mean. So this is centering, so like if we have a distribution here, and the distribution are the values in our vector, and let's say it was here, and this is 0, and maybe it has variance equal to like 2 or something like that. Then you initially shift it, so that would be this part here. You shift it by the mean, and you normalize it by the standard deviation, so you would shift it, and then you have a distribution with mean 0 and variance equal to 1. And then you have the model learn these two parameters, w and omega and beta. And this basically allows the model to move the weights wherever it wants. And maybe it moves it to a variance equal to like a half. And it moves a standard deviation equal to 1. So maybe it moves it over here. And then it would be like a thinner distribution. And that would be the output. In this case, it would be 3 values, so we would just take the mean of this, subtract the mean, take the variance, divide by the variance, and then we have a parameter omega, which would be W1, or we'll call this omega 1, omega 2, and omega 3. And you would add it to these normalized values here, or multiply it by the normalized values, and then you have your beta here, which would shift the distribution. So this is basically changing the mean, and your betas are changing the standard deviation. Your omegas are changing your standard deviation. Your betas are changing your mean, because the betas are added, so that kind of moves the distribution, and the omegas are multiplied, so that scales it. And that's all you're doing in layer norm. And you do that for each of these. Omega is shared. Omega and beta are shared across these layer norms. So you layer normalize each of these instances, but the stats for this vector here are going to be different from here. So you just normalize them to a 0, 1 distribution, and you change them by this omega and beta. Now this is a problem whenever you add more parameters, because if you just look at this, 1, 2, 3, and if we follow the old method where we just copy some of the values, so this would be 1 and 2. Let's say we copy 2 values here. We copy 1 and 2, basically adding 2 more neurons. And this obviously has a different mean. We could, this mean is obviously different from this mean, meaning that the output of layer norm is not going to keep the same function as if we didn't add the parameters, which is a problem. Now what we could do is we could just double this. So we could just have 1, 2, 3, and then 1, 2, 3, and then we have the same statistics. However, this runs into a problem where you can only double your weights, which is very restrictive, and they don't want that. So they mention all this here, and yeah, that's what they call the layer norm dilemma. You have this issue where even if your feed-forward network has the same functionality as before you changed it, your layer norm will not, unless you just double the parameters. But yeah, so they want to fix this, which we'll get into later. It's a pretty simple idea how they fix it, but there's another problem. So another problem is the depth dimension. So if we have a, this is the number of layers. So if we have our x, and we pass it through some number of layers, layer 1, layer 2, and these are all transformer layers, and layer 3, and then we get some output y. If we instead add another layer here, layer 4, then obviously this layer is going to change this output. So you can initialize these to zeros. However, like it's not, they also mention later, well, right here, that zero initialization is not a good idea. So for example, they showed that the stacking method, which is not functional preserving, so this is obviously not function preserving. You pass it through another layer, and if the layer is randomly initialized, then y is going to be different. So maybe this is y hat, and you want to retain y even if you add a new layer. But they find that the non-functional preserving outperforms a preserving baseline with initialization of all zeros. So one idea, maybe what if we initialize this to all zeros, and maybe we add like a residual connection here. But this initialization would be disgusting since it's all zeros. I mean, you can kind of do like some tricks to make sure that the gradient will update those zeros, but since they're all zeros, like you have this really bad initialization. It's not random. So they find that there was a paper that showed that if you just add this layer, even though it's not function preserving, it does better than if you do a terrible initialization of this new layer. So they conclude that this indicates that we should not pursue function preserving at the cost of bad initialization. So they are pursuing a method to initialize a new layer, but not having kind of a bad initialization like with all zeros. So that's the second issue. And they also have, that's the second issue that they mentioned. So those are the issues with the previous method, and that also the previous method. So now we can formalize what do they want to do. So specifically, they want to take the old method, which is this method here. They want to make it better and be able to be function preserving for all things they want to change. And the things they want to change, there's 4 of them. There's 4 changes to make the model larger. Changes. Let me find them. Right. No, right here. So they want to change 1, the hidden dim. So that would be the size of your input dimension, whatever your vectors are. If this was ABC. You want to change the size of the hidden dimension, or of this dimension here. It's just your featured dimension size. 2 is the feed-forward network dimension. So right after your attention, you have a layer norm, and then you have this feed-forward network. Now your feed-forward network isn't 1 layer, it's actually 2. It's an expansion layer. So you have this vector. Maybe this is your vector A. You usually expand it to some, so maybe this is A by E. So, or this is your vector 1 by E. It's just a vector. It's in dimension E. A is in RE. And then you expand this. I'll call this D actually, make it easier. D. And you expand this, usually 4D, something like that. And then you contract it to D again. And it's just an inverse bottleneck. You increase the dimensionality and you decrease it. This dimension is what they're optimizing for. 3 is the head dimension, or the number of heads. So in multi-head attention, erase this. In multi-head attention, if we just look at 1 vector here, you have your queries, your keys, and your values, like so. you would send this vector, maybe this is your vector A, through your queries, keys, and values. And this will output a vector, obviously, because it's just a matrix multiplication. That's a disgusting vector. And what you do is you split this into the number of heads. Maybe we'll say our number of heads is equal to 3. So we split this into 3 segments. And then we do, this is one vector, so I'll just get a single scalar for our queries dot keys, but that is fine. So you do your queries dot keys, and then you multiply this by the values, and you get your output. So this output will have 3 heads still, and each of these dimensions here is split. Actually, I think it would be better to show it like this. So if I take this, and instead of showing it like I showed before, I'm going to stack these. So we split it up and we stack them. So we have this. So maybe our dimensionality is d. Then this would be d by 3, d by 3, and d by 3. This still represents one vector, our vector A, except it's split into 3 different parts. So our queries.keys transpose would give us it would give us 3 different matrices instead of just one. And whenever you multiply it by the values, it would also give you 3 different vectors here. So these 3 different matrices basically kind of represent parallel computations you can make. It's very arbitrary, but in terms of, I don't know, in terms of words, maybe this quote head only looks at like verbs or something like that. Or this head here only looks at like nouns or something like that. You can kind of think of it in that way, but they do different computations, and it's basically getting more representation power out of your attention mechanism, because usually you would have one matrix, but if you split the dimensionality, it could also just have like this. It could go back to the default behavior, or it could use these heads to have more representation power. And basically, you have these, it can kind of pass information into these individual buckets here in this vector to do different whatever computations it wants to do in that head. So it's just parallel computations to give it more representation power. But then you stack these together to give you this output vector, and then you multiply this by an output matrix to basically combine the information here, and then this gives you your final output, which is O. So that's multi-head attention really quick. But yeah, they want to change the head dimension, which is just adding another head. So they call it head dim, but it's actually more like number of heads. And then 4, they also want to change the number of layers. Layers number, yeah. And that's just adding this part here. So those are the 4 changes they want to make. Now, this one here, this one, those are done by the previous method. You can easily do those with the previous method if you get rid of the layer norms. This method, or 3 and 4, cannot be done with the previous method. Obviously, this one cannot, because you're adding another layer and you have this bad initialization, like we said earlier. And this one cannot, because it's similar to this layer problem here. If you add another head, say we only had 2 heads here, if you add a third head, then obviously there's going to be more information in this weight matrix. So that's what they want to optimize for whenever they are, or that's what they want to add whenever they're expanding the model from a small model, maybe with a small number of heads, a small number of layers, to a larger model with more heads and more layers. So they do this with a lot of masking. So we'll get into how they do each of these methods. First, how do you expand a fully connected layer? It's pretty simple. So if we go back up here, and we have our 2-part vector, instead of, so it's a very simple algorithm or procedure, I would say. So instead, we will change these back to their original dimension, or to their original weights. So that looks like that. Now, let me go to the picture. Right, so they add a new weight, which they call x prime, or a new node, not a new weight, a new node, and all they do is they mask it. So this would be, say, we'll call this W0 and W1, and x prime is going to be equal to, let me go back down here to see exactly how they formalize it. It will be C times the activation of W0 I, all right, I'm gonna make that W1, W1, W2, didn't zero index it, W1 I1 plus W2 I2. So you send this through your activation, and then you multiply it by your mask. And the mask will be a 1 here, a 1 here, and it'll be initialized to a 0 here. So your output is going to be 0. This will just be zeros. Now your weights are randomly initialized because your output will be a 0. And since this output is a 0, these weights can also be randomly initialized. Maybe we'll call this W3 and W4. Now, this value, y1, will be equal to x1a plus x2b plus x prime w4. And this will be equal to x1a plus x2b plus 0 because this is initialized to 0. Now we have a new node here with new weights, but it doesn't do anything. So what they do is they slowly change this C from 0 to 1 over time, according to some scheduler. And and it's some linear interpolation between 0 and 1. And they do this over, say, 5,000 steps. So at step 0, this would be 0. At step 5,000, it'll be a 1, meaning that this node is fully active and can send information to its fullest potential, I suppose. And this is the model doesn't learn this. This is a scheduler that is placed by the person implementing this algorithm. So over time, maybe let's change it to 0.1, and this would instead be 0.1 times W4 x prime. And maybe you increase it more and more, and it eventually becomes 1, and now you have this full W4 x prime as time goes on. So that's how they increase this. So I mean, it's a very easy method. Yeah, and they say it works, or that's basically all they do to change this part here. It's just you can add an arbitrary number of nodes, and as long as you mask it with 1s with the old weights and 0s with the new weights, and slowly interpolate 0s to 1s over time, then you're all set. You got yourself a working feed-forward layer that implements this, that has the same function by adding new parameters. Now, as for the layer norm is the same thing. They use masking again. So if we look here, they mask. So this is the mean and standard deviation that you have to normalize the, if we go up here, to do your initial normalization. So this normalizes it to a distribution with mean 0 and standard deviation 1. And if you look at this, you can see they mask it by a mask C, which is 1 if it was part of the old weights, or if it was part of the old dimension, and 0 if it's part of the new. And that's how they initialize this. And you can see that you sum, like whenever you mask this, you basically only get the information from the old data. and you divide by the sum of C, and the sum of C will just be the number of items in your old data. So this mean and this standard deviation are not changed because of this mask. So you mask it by multiplying your x's by zeros if your x's are new data. So if we have if we go over here, then maybe we have A and B, and that's our old data, and then we have n sub 1, and that's our new data. Then our norm, our initial norm for 0, 1, where the model doesn't have its parameters, all we do is take the old parameters and calculate the mean standard deviation on the old parameters, but we don't look at the new parameter. And then we normalize all the values in this vector by this mean standard deviation, including the old including the old weight or the old values and the new values. Then we know that the second part is you use your beta and omega, and they just copy the first d values. So we know that our omega and beta are vectors of size d, and initially this would have been maybe your A and your B. Maybe this is your omega and this is your beta. And this first part represents the value you, omega was the multiplicative. So this part represents the value you multiply by A. And this value represents the value that you add to A. And the same for B. But you add this third part here. So you just copy the weights for the old you just copy the weights for the old mean invariant shift, and for the new one, you initialize the new weights to arbitrary values. So it's just an arbitrary value. That would be your n's. So these n's are just an arbitrary value. Yeah, so you can just make this an arbitrary value. Maybe you initialize it randomly. And in this case, your A hat and your B hat, which is me kind of showing what happens after the second normalization. And the second normalization comes from this part up here. If I go back up here, the multiplying by this weight and adding by this weight. So just layer norm, normal layer norm behavior. And then you add this new weight here, which is randomly initialized to some arbitrary value. Now you have this output here where your A is maintained and your B is maintained because the mean and standard deviation were only calculated from those A and B. Your N, on the other hand, are not. But if you just mask the output, so by C again, where C would be equal to 1 here, and 0 here, then you're all good. And now you have this maintained output. And you may be wondering, how do we shift this over time from 0? How do we shift this over time? Well, we have a mask here, so 1, 1, 0. And if we just interpolate this 0 again, where we have zeros where the new dimensionality is, to a 1 over time for both the input and the output, then the statistics for the input, the mean and standard deviation that you shift by to make it a 0, to make it a normal distribution, 0 mean, 1 variance, will slowly take into account these new, the new dimension, the new parts of the vector. And the output will slowly consider the new parts of the vector. So that's the layer norm solution. It's just masking the input and masking the output and slowly interpolating from 0 and 1, from 0 to 1. And you can see that here. 1 for the old dimensionality, 0 for the new. And that's literally all they do. As the training goes on, we gradually increase the last values of C to 1. So yeah, you're just increasing it from 0 to 1. Now, how do you grow self-attention heads? So this requires masking as well. And I've kind of done a little bit with masking, the inattention. It's a little annoying. But to do this, if you have, say, these queries, you have these keys, and you have these values here. Now, let's say we have masks for our queries, keys, and values, and the masks look something like this. Then these would represent this mask here would represent the new dimensionality. Maybe you have a vector with 3 parts in it, and this last part here is the new dimensionality that you add to your embeddings. Then you would want to mask this part after the feed forward layer. So this would just be multiplied by c. C is equal to 1, 1, 0. So you'd split this into 3 parts because it's a 3-dimensional vector. And you have that here, 1, 1, 0. C is equal to 1, 1, 0. Now, whenever you compute your attention here, this is your keys, these are your queries, you want to mask it in a way where you have no information from the masked keys. And so basically your keys have no information for the masked component. So in this case, it would be this last part. Maybe if this is word A, B, and C, then this would be A, B, and C. And this would be A, B, and C. Then you want to mask this entire vector after the softmax. And you do that because you don't want this vector, you don't want it to have any information. Well, assuming you pass it with no information. So you basically don't want it to kind of send information, and you don't want it to receive information from this. So you mask this part here because you don't want C sending information to A and B, basically. Therefore, it maintains this 2x2 matrix here. And notice this 2x2 matrix here is the same. Like if we had the C's here, and if we didn't have the C's here, so if we just get rid of the C's, then you have this 2x2 matrix, which is what the softmax would have been before if we didn't add the C. And since C is our new dimensionality, then we can just mask C and maintain this dimensionality. And this would just be by a vector C, where C is equal to 1, 1, 0. And this is going to be a common theme. You just mask it with 1s on the old dimensionality and 0s on the new. Then you multiply this by the values here. And you will maintain your output because your values are going to be a linear combination. And I do want to note, you do this masking before the softmax because whenever you do the softmax here, if you were to do it after the softmax, and the softmax would have already taken into account this value. So you mask it before the softmax, and then the softmax only looks at these two values here. So this value will be maybe A, and this is AB, BA, BB. Then your values will be composed of these linear combinations according to these weights here. And yeah, assuming that these are masked, then your output values will be fine. And then you can just send this through a weight matrix and you get your output. So normal behavior, except you're masking your attention, you mask your attention by the C value, the C vector, 0, 1, 1, 0, according to the new weights. So that's all they do. And they also mask the values because you have to mask those according, like the values are a linear combination, so you have to make sure that the last part here still doesn't have, is still masked. Yeah, so that's how you would mask your self-attention. If you want to just mask a head, on the other hand, let me do that. Well, they show that here. If you want to mask a head, it's very similar. All you have to do is multiply all 0 mask C to the value vector, where the value vector is multiplied by this mask C, and C is this common thing you keep on seeing. You multiply it by the value output, and you basically say 0 if it's a head that is new, and 1 else. So if we scroll back up to, oh, I think I erased it. Oh no, right here. If this was, say, our old head here, like we have the 2 parts that are old, then you would mask this third part here, and you mask this third head here. You mask the third head here, and you also mask it again, and your weight will take in zeros here, and in your output, it won't have the information from this last head here because you masked your last head with a 0. And like usual, you just linearly interpolate your masking from 0 to 1. Yeah, it's just multiplying the output head by 0. So that one's pretty easy. It's just like adding a new dimensionality, except the dimensionality is a little bit larger, but it's the exact same idea. And finally, we have depth growth. Depth growth is pretty easy. If we look over here, if we have a layer here, maybe this is our output. This was our old output, and this is the output of the model. But if we add a new layer, then this model output will go through this layer. Now, the idea here is we take this output here, and we multiply it by a mask. Oh, really? We multiply it by a mask? I've seen that before. Yeah, so we multiply it by a mask, and we multiply the input by the opposite of the mask. So we start off with c is equal to 0, then, and we look over here, then the output of the layer will be 0 times, so it'd be 0 times the layer of x, so it'd be 0 times the output of the layer, and then it would be 1 times the input of the layer. You can kind of see this as like a residual, where we initially just take this value and we send it up here. And then you interpolate this from 0 to 1, and slowly, maybe you get to like 0.5, then it'll take half information from the input, or from the input, and half from the output, and this slowly becomes 1 and this becomes 0. So this residual slowly fades away until this layer becomes complete, I guess, until you reach some amount of time steps where this C becomes a 1. And there we go. Those are all the parts that we wanted to achieve, and we can grow them by maintaining functionality by just masking and growing the mask from, or changing the mask from 0 to 1 over time. Now, the way they change it is kind of seems arbitrary to me. I feel like there should be more experiments with it. But yeah, they have this heuristic over here, but it feels more arbitrary than that. But they do have some notes here. So the first note is you want to grow layers in the later stages. Larger number of layers severely harms tau and gain in alpha. We would better grow layers in the relative late stages. And tau and alpha are just the heuristic they use, but I don't think it's that important. Another note is start from a large hidden dimension. Larger hidden dimension brings significantly better heuristic for shallow models. We should not start from a very small hidden dimension. So if you have a large hidden dimension, then it does a lot better for small models. So might as well just start with a large hidden dimension because it doesn't, growing that from small to large doesn't really, like it hurts performance. Feed-forward network does not matter too much for the initialization. So if you initialize the, if we go to the feed-forward network part, the inverse bottleneck part, it doesn't really impact, like the initialization of that value doesn't really impact it that much. And we can see all these up here. If we look at these graphs, this is the, this is at the initialization, basically. Wall time in seconds for 600 seconds. This is some arbitrary amount of time, and they just kind of stop it here. And they say if we initialize with 3 layers, 6 layers, 12 layers, or 24 layers, how does that affect the initialization? And basically, you want this to have fast convergence upon initialization, because we're going to increase these values anyways. And if we look here, if we start with 3, then it converges really fast. So if we just have 3 layers, then it converges on the loss really fast. But if we have 24 layers, then it converges really slowly. And that's why they say it would be best if we just start with a small number of layers and then we add them over time, because it will converge faster. And this is wall time in seconds. So it's not, maybe it's the same number of steps and this actually goes a lot lower, but they're looking at wall time in this case, in this paper. And here's the hidden dimension, and they note that if you start off with a low hidden dimension, then the convergence is not as good if you start off with a high hidden dimension, and that's the second note that they made. And the third note that they made is the feed forward dimension doesn't really matter that much. You can kind of see that here. They all converge about the same rate. A smaller one may be better, but not that small. So it's about the same. And the last part, the head number. You don't want to start off with a large number of heads because it also has slow convergence at the beginning, which is interesting. But 8 or 12 works. So those are some of the things that they show. There's some of the ablation kind of things they show. And finally, so that was the scheduler part, kind of arbitrary. I think there should be more testing on that. And finally, the initialization. They say they find an initialization using a normal distribution of 0 and 0.002 works well. There you go. And to initialize the optimizer, we copy stored moving averages of atom W from the original optimizer for existing weights and start from 0 average for the new weights. So you just copy the weights over and you start with a 0 average for the new weights. Makes sense, I think. It doesn't have any momentum, so it's not changing the optimizer at all because it has a 0 average. So now, with all that out of the way, let's just get to the results. They have a little bit. I think they should have more results. So we already got to this ablation part. I guess show this. So basically they're looking at BERT and BERT large. And for pre-training, they have, they're looking at this Wikipedia corpus and this book corpus. And they use a linear increase from 0 to 1 using 5,000 steps for each growth. So let's look here. Here are the growth schedulers. It feels kind of arbitrary to me, but they initially increase the dimension, the hidden dimension. That would be the feed forward dimension. This is FFN. Then they increase the number of layers. Then they increase the dimensionality of the input vectors. Then the number of heads. Then the number of layers again. I mean, feels arbitrary. And this is base and large. And then this is the second scheduler that they use, and it feels just as arbitrary to me. But it seems to work well. So if we go here, we can see some of the results. So if we look at these results, full B is kind of the baseline. That's what they're trying to beat. And the goal is to beat the wall time, but get an equal to or better accuracy on the benchmarks. And they look at around half the time. So if you train this for half the time, then you get very similar results. If you look through these results on the benchmarks, they're very, very similar. In some cases they're better, in some cases they're worse, and that's probably just due to random noise. Probably just some entropy in training. So it does look like with about half the time, you can get just as good results. And if you train for the full amount of time, you can definitely do a lot better. Probably. It would be cool if they tested that as well. And we can see here for the large model, it basically outperforms the base model with half the training time in all the benchmarks, as you can see here. And yeah, those are the benchmarks they tested on. I wish they showed more benchmarks, but yeah, there we go. That is the paper. It's just masking. That's basically it. Yeah, 2 times faster language model, or 2 times faster language model pre-training via mass structural growth. Exactly what they said. Just masking things and growing it according by using that mask. So that's the paper.